All right, let's get started. I should have the test graded because they're uploaded. The test they're harder to grade, takes longer. I have to use something called a speed grader, and it's a pain to use, but it is what it is. So I should have your test back maybe by Wednesday of next week. So, all right, Unit 3. Unit 3 is on carboxylic acids, esters, and lipids. The lipids are one of the older units of study, probably of everything we're going to cover today, lipids. Okay, so first of all, you need to know what an acid is. All of you have had 305, but you might not have remember what an acid is. So there's a lot of definitions for acids. In here, this is the definition we're going to be using. Okay. Excuse me. So an acid, one has to have a hydrogen group on it that will disassociate, come away from that chemical. Now, as you know, there's a ton of hydrogens in organic chemistry, but only if that hydrogen disassociates is it called an acid. And there are two kinds of acids. Strong acids, 100% for strong acid. There are only 7 of them in the world, at least as of today. 100% of the hydrogen comes off of the parent chemical. A weak acid is a weak acid. Not all of it comes off. Some of it stays on the parent chemical. Okay. So you all are familiar with strong acids. There's hydrochloric, sulfuric. We use sulfuric acid a lot in organic chemistry. These are the 2 main ones you're going to be running across in this class. The weak acids, there are probably a couple million of them. So we went from 7 strong acids to millions of weak acids. And most organic acids are weak. Okay, an example of that would be like acetic acid. Aspirin. Salicylic acid. There's just bunches and bunches and bunches. And then there are the fatty acids. Okay, so with the acid again, you've got to disassociate the hydrogen. Otherwise, it's not an acid. So the carboxylic group is the acidic part of the molecule. And this is the hydrogen that comes off. So this is a combination of an alcohol and a carbonyl group together. You've probably heard of acetic acid. You might not have heard of formic acid. Whenever you get stung by an ant, a red ant, that's what they inject into you. It's formic acid. And it's very interesting, the derivation of formic acid. There was a 150-ish years ago, there was a chemist and he had a son. And he walked out in the backyard and his son was boiling red ants over a fire. And of course, he was disciplined and everything. And then his father decided to look at the boiled water afterwards. And he found formic acid. And formic in Latin is ant. And that's how they get the name formic acid. You've all heard of citric acid, lactic acid. They're much more complex weak acids, but they're very common. Oxalic acid is interesting. It, whenever you eat raw spinach, you'll notice it's slightly gritty. That's the oxalic acid. Now, fatty acids are long acids, anywhere from 12 to 20. And they get much longer than 20. They go up to like 28. And they're characterized by a big, long, nonpolar tail with a very polar acid end. Now, these are stark contrasts in polarity. We're going to find that the acid is even more polar than an alcohol. And then, of course, we have a long alkane end, which is the exact opposite of that polarity. Now, we're naming the acids IUPAC convention-wise. We count the backbone. And that goes with our normal naming conventions. And then we put it oic acid on the end. Now, a lot of biologists and biochemists don't use the IUPAC name. They usually use common names. And the reason why that is acids have been around for so long. And biologists tend to not go by, and not molecular biologists, talking about regular biologists, tend to go by more common names when they name chemicals as opposed to the IUPAC names. IUPAC can be quite complicated. Okay, as far as benzene is concerned, we're going to be naming them off of benzoic acid. And there will be branches off of that. Carbon number 1 is always where the functional group is on the benzene ring. It's always number 1. Now, again, carboxylic acids are extremely polar. The reason why they're extremely polar is because they disassociate that hydrogen off and it becomes ionic. And ionic things are tremendously polar. Frequently, if you just have a liquid carboxylic acid, which is 100% like 100% acetic acid, what happens is they end up forming something called a dimer, which is what this guy here is. So the carbonyl group, the oxygen on the carbonyl group is partially negative. The hydrogen on the OH group is partially positive. And that's where they get that strong attraction. Liquid acids have a very high boiling point and melting point because of this interaction. We look at some similar molar masses or molecular weights. You can see that the carboxylic acid boiling point is quite a bit higher than the corresponding alcohol. In fact, it's much higher. And again, that's because it's so polar. If we look at a graphic representation of that, the blue line on the very top are the acids. Now, in a little while, I'm going to talk about something called an ester, and that's going to fall lower than an acid. Now, because the acids are extremely polar, they dissolve in water quite readily. Like when you buy vinegar at the store, that's 5% acetic acid. And you cannot see the difference between the acetic acid layer and the water layer. They're totally immersible because their water is very polar and these guys are correspondingly polar. So like dissolves like. Now, just like with alcohols, 7 carbons with an alcohol, a 7 carbon tail on an alcohol, primary alcohol, it becomes insoluble in water. Anything shorter than that, they dissolve in water. There's a similar phenomenon with acids. We have, in this case, we have the same carbon 7. If the tail is 7 carbons long or more, it's insoluble in water. So that's the cutoff. Now, unit 4 is on nitrogen bases, and they're the opposite of unit 3's carboxylic acids. So you need to know what ionic state the acids are in different pH environments. So if we look at pH values of greater than 7, that's an alkaline environment. What happens in an alkaline environment, say we have propionic acid. what happens is it becomes ionized. And we talked about this when we were talking about phenol. Phenol is a weak acid. So in an acidic environment, pH less than 7, nothing happens to the acid because there's nothing in an acidic environment that can pull off that hydrogen. So when we get to unit 4, we're going to characterize the base part of it. And acids and bases act totally opposite one another when you change the pH from an acidic environment to a basic environment. They swap out different things. When a strong base is around a weak acid, like a carboxylic acid, what happens is that OH on the strong base grabs hold of that hydrogen on the acid and forms water. And this is called the acid salt. So when you name an acid salt, first thing you do is you name the corresponding cation that came with the base. In this case, it's sodium hydroxide. So what you end up with this, say this was we were taking and putting a strong base with acetic acid. What happens is, again, this guy grabs that, forms the water, and we're left with the acid salt. To name the acid salt, what you do is you replace this with ATE. So benzoic acid becomes benzoate. Acetic acid becomes acetate. And you have to name the so what comes first is the cation name from the base. In this case, it was sodium. And this is the backbone plus 8. So say we had a so this is 1, 2, 3, 4, 5, 6. So this would be hexanoic acid. If we added a strong base like sodium hydroxide, we end up with water. And this would be hexanate, sodium hexanate. Okay, so this depends on the length of the backbone. So from carbon 7 on, this is true, solid room temperature. Usually soluble, but again, it depends on the backbone length. Now, these are 3 acids you're going to need to know: palmitic, oleic, linolenic, or linoleic. You're going to be learning about 10 fatty acids, and they're very common in nutrition. There'll be some omega-3s in there, and you're going to learn a new naming system for acids as well. The omega-3 is what nutritionists frequently use, but it's not used by biochemists. Biochemists uses a much more precise way of naming fatty acids. Now, when we made salt in lab, we were doing just this. We were taking well, I'm going to get to that in a minute here. We talk about esters. You were taking an ester, pulling the fatty acid part off, and you were left with the sodium salt of the ester. Now, ivory soap is a lye soap. Sometimes they use sodium hydroxide, sometimes they use potassium hydroxide, but the fat is exposed to strong acid. What you end up with is a salt of that fatty acid. And because the salt is even more polar than the bare acid. But this is the deal with a soap. There's 18 of those. That end is extremely polar because it's ionic. And with a long, long backbone, an alkane backbone, it's extremely nonpolar. That's called an emulsifier. So on your next test, one of the questions is going to be, can this act as an emulsifier? I'll give you the molecule. And what you need to look for is it super ionic? Some part of the functional group on that molecule, is it ionic? Secondly, you need to have a nonpolar part of the molecule. And if you have both those on the same molecule, it's an emulsifier. And if the molecule happens to be a triglyceride like fat, then they call it soap. But the more generic term is emulsifier. Sometimes they're called also surfactants. Like they'll add a surfactant to paint so that it sticks to a lot of things. If you mix the sodium salt with the acid, you end up making a buffer. And in Chem 401, you do that. And you actually can calculate what the pH buffer is if you know what acids and acid salt you're using. And it's kind of a tricky calculation because you have to use logarithms. Now, when you mix an alcohol and an acid together, you form an ester. Esters are extremely common in biological systems. You'll see them all over the place. That's what makes up fat. Fat's an ester of a long backbone fatty acid. Their acids tend to taste sour. Esters are the exact opposite. They tend to be fragrant and have a very characteristic flavor, not sour. So if you've ever made a vinaigrette, usually it's 2 part oil, 1 part vinegar. If you put too much vinegar in, your vinaigrette tends to be sour tasting. And that's because you're tasting that vinegar acidity. Esters do not have that sourness. Now, the process to make an ester is called esterification. So you need an acid and an alcohol. And the alcohol could be an aromatic alcohol also, not just, Okay, so under heat and acidic conditions, we make the ester. Notice, it's a two-way street. And if you take an ester under basic conditions, you break the ester apart. So let's make some esters now. Again, you need an acidic part and an alcohol part under acidic conditions. So if we look at this guy here, so this is a 2-carbon alcohol, 4-carbon acid. When those come together, we're going to end up making a ester. So this is the ester. Now, in lab, we're going to be doing this. What's interesting about this particular reaction, butanoic acid smells badly. It smells like a dung. It smells like a chicken coop inside. It's really, really smelly. Ethanol really doesn't have any fragrance. When you mix them together, though, to make an ester, you end up making strawberry imitation strawberry flavoring. And it's such a contrast. When you take butyric acid and add a methyl alcohol, like methanol, you end up making wintergreen. And it's so dramatic, the difference between the two. It's really a cool lab. Now, naming the ester. There are two parts to naming it. There's the alcohol part and the acid part in the name. So we have so in this case here, this strawberry flavoring, we started with the ethanol, so that's going to make this ethyl. And we ended up with starting with a 4-carbon acid. So that's butanoate. And it's going to look like that. Here's what salicylic acid looks like. That's what we use to make aspirin. So it's both an alcohol and an acid together. So sometimes when your aspirin gets old, it has a vinegary smell to it. Or if you buy cheap aspirin, brand new, it's got a vinegary smell. What happens is when it starts to break down, it kicks off the acid and the alcohol from which it was formed. Now, there are 3 ways to make an ester. In lab, we're using the middle one, but there are 3 ways to make an ester. The poorest way is you start with the acid and the alcohol, like up here. Acid, alcohol. You get the smallest yield with that. But there are 2 other ways to make an ester. Using the acid chloride or the anhydride. Now in lab, we use the anhydride to make aspirin. We could have also used the acid chloride. The acid chloride has extremely reactive. You get the best yield using the acid chloride, but the shelf life on acid chlorides is very small because it's so unstable and reactive. The anhydride is much more shelf stable. The yield is middle between using the bare acid and the bare alcohol. So frequently on tests, I'll say, make this 3 different ways. I'll give you okay, so make that ester 3 ways. Now, how do you know you have an ester? This is the OCO thing again. So okay, if you've got that, you either have an acid or an ester. Okay. If it's no, you have an ester. If it's yes, you have an acid. So we have OCO again. And instead of doing acetals and ketals, one of the oxygens is going to be double bonded. And it's both the single bonded oxygen and the double bonded oxygen come together on one carbon. And there's no fancy name like with acetals and ketals, we had anomeric carbons. There's no fancy name for this carbon. It's just the one that everything attaches to. Okay, so we have OCO. If the answer is yes, then it's either an acid or an ester. And then if it's an OH, it's an acid. If it's not an OH, it's an ester. Okay, so let's name this guy. Okay, we have 2 carbons here, 3 carbons there. So we name the alcohol part first. So that would be ethyl. Propanoate. So this is the alcohol part, acid part. Okay, how do we make this? 3 ways. One way is with taking the acid, propionic acid, plus the alcohol, that would be ethanol. And we get the ester. Okay, so that's one way. Acidic environment, heat. Okay, so that's one way. Another way is to use the acid chloride. Same alcohol, and the third way is to use the anhydride. Now think of the anhydride as 2 esters. So here's an ester, and there's an ester. So we're going to have a 3-carbon acid anhydride. Okay, so this is so this would be the dipropanoic anhydride plus the ethanol. Okay, so this, using the acid chloride, gives the highest yield. Okay, so starting with just the acid and the alcohol gives the lowest yield. Acid chloride plus the alcohol gives the maximum highest yield. And then the anhydride is in the middle. So what dictates these yields is the stability of what you're starting with. Because the acid chloride is so unstable, it wants to react. With the acid is fairly stable. So that's why you have to force it with acid in an acidic environment with heat to get it to go to the ester, because the acid originally is stable. So this is purely based upon stability of acid. Okay, so that would be how you'd answer that question. Now, all three of those gives you the ester. When you're using the acid chloride, you generate, along with that, hydrochloric acid. When you're using the anhydride, you end up generating the acid from which the anhydride was made. So if we had 2-carbon acid chloride, 2-carbon alcohol, we're going to end up with a plus HCl. The anhydride is made up of 2 acids coming together to form an ester of one another. And in this case, it's 2 carbons long. It doesn't have to be the same acid. You can have different length acids coming together to form the anhydride also. And you see that a lot in biological systems, where the originating alcohols are not the same length at all. They're very different. Okay, we're not talking about plastics. We're only talking about biological polymers. But esters are used a lot in the plastic industry. Okay, I already talked about how to name the ester. So to name the first one up there, it's going to be methyl. So it's going to be methyl ethanoate. This one here is going to be phenyl. Phenyl butanoate. Now notice we're using phenyl and benzene here. So when the alcohol is an aromatic, we're going to be using the phenyl. When the benzene is the acid, then we use the benzoic acid base. And that is a bone of contention a lot of students get confused about. When do you use phenyl? Okay, so esterification is when you make an ester. Ester hydrolysis is when you pull it apart. And that can be under so say we start with this will be ethyl. Propanoate. Okay. Now, when the pH is low, pH under 7, what you end up getting, so this would be like in acidic conditions, what we end up getting is the starting acid protonated though. So this would be propanoic acid plus the 2-carbon alcohol. If the pH is greater than 7, what we end up with is the acid's salt. So this would be, say we're using sodium hydroxide. This would be sodium. So that would be sodium propanoate. And this would be ethanol. So you need to know this. And if the original acid was a fatty acid, a big long carbon backbone, we make soap. And this process under alkaline conditions is called saponification. So when you saponify something, one, you need an ester. You can't saponify anything if you don't have an ester. And you have to be in an alkaline or basic environment. So when we made soap, we started with an ester. That was the fat. And we added to that sodium hydroxide. And then it yielded the acid salt, also known as soap. Um, two carbon acid, two carbon alcohol. Here we have acidic conditions, so we end up with the acid and the alcohol. Two carbons, two carbons. Okay, here we have, this would be ethyl benzoate. What we end up with is benzoic acid plus ethanol. That's under acidic conditions. So under basic or alkaline conditions, we end up making the acid salt and the alcohol. So here we're starting with a one carbon alcohol and a benzoic acid base. So we end up with the, again, pH is greater than 7. We end up with the acid salt, sodium benzoate, because we started with sodium hydroxide, and then the alcohol. Okay, now, for those of you who are interested in something called a mechanism, this is how it works. But you're not responsible for this. Well, you have this guy here. Remember we talked about the carbonyl group, this is slightly negative, that becomes a little positive. So that OH group is attracted to that carbon. And that's how this process starts. But no mechanisms. Okay. So if we start with this acid, carboxylic acid, weak acid, in water, it's going to disassociate a little bit because it's by definition acid disassociates. In a base, you're going to form the salt. If you add an alcohol to carboxylic acid, you end up with an ester. In a basic environment, you're going to end up saponifying that ester. So this would be saponification process. And if in an acidic environment, you're going to end up with the acid plus the alcohol. These are the acids, very common fatty acids you need to know. There are, what, 10 of them? 8 of them. And if you buy omega-3 fatty acids at a health food store, you're going to look on it and it'll say EPA and DHA. They're not going to say icosapentaenoic acid or docosahexaenoic acid. They're not going to say that. They're going to say THA or EPA. Now, what time is it? It's 1:30. Okay, let me go into this naming here. Okay. Versus the omega naming. Okay, if we look at a simple fatty acid, oleic acid. Okay, they found oleic acid in olives. That's hence the name oleic. So the fat in olive oil is made up of oleic acid. So you've got 3 things you need to know about each one of these. One is the delta naming. Another is the omega naming. And the third thing is the UPAC name. Versus the common name. So let's look at oleic acid. Okay, so this is the IUPAC name. That's the common name. They have a shorthand way of writing it, OA, for oleic acid. This is the delta. And that's the omega. So oleic acid is considered the healthy fat, part of the Mediterranean diet. There's a lot of current research going on regarding fats, and there are good fats and bad fats. The good fats are single double bonded fats like oleic acid. Also, omega-3 fats. I'm going to show you how they name stuff. Bad ones are totally saturated, like stearic acid. You get that from pork and beef. probably lamb as well. Okay, so oleic acid is 18 carbons long. So we're going to go okay, that's 18 carbons long. And the double bond is on carbon number 9. Now that's trans, normally it's cis. So this would be trans oleic acid opposed to cis oleic acid. Okay, so notice there's an 18:1 delta 9. (18:1) delta 9. So 18 is how many carbons are there? How many double bonds? And what carbon number is the double bond on? Carbon 9. Okay, so that's the carbon backbone. Number double bonds. That's the carbon number from the acid end. Also notice it's an omega 9. So omega 9 it's 9 carbons from the end of the fatty acid. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. It doesn't say anything else. So when you say like linolenic acid is an omega-3 fatty acid, it doesn't say how many double bonds are in linolenic acid. It just says that the first one occurs 3 in from the end. So that's why biochemists don't use the omega. Nutritionists do. The biochemists use these guys. The nutritionists use the omega. Consumers never see this delta stuff. You look on a packaging label, you don't see the omega either. You just see the common name of it. But in nutrition articles and journals and stuff, they'll be using the omega designation. You hear it all the time, omega-3s, omega-3s. Now there are omega-6s, omega-9s, and omega-3s. 6s and 9s are easy to come by. Omega-3s, you get 2 sources, animal and plant. The animal sources are cruising fish like tuna, salmon, mackerel, sardines. All those fish are cruising. In other words, they're using their muscles all the time, as opposed to bottom feeding fish would sit on the bottom and wait for the food to come floating by, and then they grab it. So they're not, it's totally a different feeding modality. And then the plant source for omega-3s is flaxseed. Flaxseed oil has omega-3s in it. Now, if you're a vegetarian, it's hard to get omega-3s because flaxseed oil, our bodies don't absorb that very well. So you have to eat a lot of it. Okay, I'm going to end this here. And on what I'd like you to do over break is to start looking at those 8 fatty acids I want you to know. You have a whole week to do it. When we get back on the Tuesday after break, I'm going to do some more examples like this using the delta. Oh, one other thing, we need to name it. Okay, there's a common name, which is oleic acid, and the IUPAC name is going to be octa-8 decanoic. Okay. Octa. So it's 9-octadecanoic acid or oleic acid. Yeah, so I went through everything. Okay, we have the structure itself. We have the delta naming, we have the omega naming, we have the IUPAC naming. Okay, so work on these over break. Your next test is going to be in-class test. Okay, all you guys have a nice break. Relax. I am going to relax. My friend is getting a new dog tonight, a little bitty 8-week-old puppy. And yesterday we were out shopping and she got this little dog bed that's like a cave. And this woman is very frilly. She likes pink stuff and flowers and all that stuff. So guess this poor little dog, and it has to be a female, of course. This poor little dog's going to be, and she even bought a dog stroller. It's got a little zipper thing on top with holes in it, and stuff. And so that's what's coming tonight.